Okay, so this is part 284C3m1b7c8e13c9b. Okay, line 22f1fa19c3m1b7c8e13c9b, dielectric, capacitor, crystals, core, UFO 5G Wow Seti. There's our alien radio signal. This one's about the UFO core engine keyword research, dielectric, from a previous video about quantum transport. So it's continuing on the, I'm continuing to research the words. So December 7th, 2012, I was working on this. Today is January the 8th, 2013. The keywords to research from the data from a previous series of filmed videos ago. Sorry. From a while ago, basically. Probably about 60 videos back, okay? So it's line 22f1fa19c3m1b7c8e13a, quantum transport, nanodevices, UFO 5G Wow Seti. Line 22f1fa19c3m1b7c8e13c9a, lead, zirconate, titanate, dielectric, ceramics, 5G Wow Seti. That was the previous video that I just filmed, okay? So it started with the 13A and now we're up to 13C9. So the keyword lead, zirconate, titanate leads to dielectric. So December 26, 2012. My thoughts from a previous video. Actually, this is kind of a formula thing. Power from the crystals with electricity, dielectric, semiconductors, and capacitor. For the UFO core spaceship engine design ideas found in the WOW formulas in lines 22. In line 22 alone, it has hundreds of videos, probably 100 or 200 videos just in that one line alone. And it's talking about the core, the engine, and the formula mixtures for the actual fuels that go into the engine, and they're self-regenerating fuels, so they never burn out. So more keyword research dielectric continues in the next video from line 22. F1fa19c3m1b7c8e13c9a, lead, zirconate, titanate, dielectric, ceramics, 5G Wow Seti. So keyword is dielectric. Quote diagrams from the blog. Vacuum permittivity, capacitance equals C, dielectric permittivity equals E, and K equals C. Oh, there's the equations there. The dielectric constant of a material provides a measure of its effect on a capacitor. It is the ratio of the capacitance of a capacitor containing the dielectric to that of an identical but empty capacitor. Quote from blog. An alternative definition of the dielectric constant relates to the permittivity of the material. Permittivity is a quantity that describes the effect of a material on an electric field. The higher the permittivity, the more the material tends to reduce any field set up in it. Since the dielectric material reduces the field by becoming polarized, an entirely equivalent definition is that the permittivity expresses the ability of a material to polarize in response to an applied field. The dielectric constant, sometimes called the relative permittivity, is the ratio of the permittivity of the dielectric, how many times do they have to write this word here, to the permittivity of a vacuum. So the greater the polarization developed by a material in an applied field of given strength, the greater the dielectric constant will be. There's no standard symbol for the dielectric constant. You may see it referred to as KE, E apostrophe, or ER. And the TLPK shall be used to avoid confusion with the absolute permittivity, which may also be given the symbol E. The two definitions of the dielectric constant are illustrated by the diagrams below. The green arrows represent the electric field. In general, the more available polarization mechanisms a material possesses, the larger its net polarization in a given field will be, and hence the larger its dielectric constant will be. The dielectric constant of a material and its refractive index are closely linked by the equation K equals N squared. Click here for the derivation, whatever that means. Let's see what it says. This is what I like about OneNote. You click on a link, it takes you right to it. So it's at www.deutpalms.ac.uk. So this is the dielectric constant refractive index. So basically he goes to the speed of light in a vacuum, the speed of light in the material. So you would go there to look at his equation, okay? Let's go back here. However, care must be taken in applying this equation. It is only strictly accurate when the dielectric constant and the refractive index are measured under the same conditions. Specifically, since the dielectric constant can vary significantly with frequency for reasons discussed in the next section of this TLP, we must measure the dielectric constant under alternating current at the same frequency that we measure the refractive index at, the frequency of visible light of 10 to 15 Hertz. However, quoted values of the dielectric constant normally refer to the static dielectric constant, that is, the dielectric constant under direct current. This is often very different from the value of the dielectric constant at 10 to 15 Hertz. This exception is for materials that possess only the electronic mode of polarization. For these materials, the dielectric constant does not vary significantly with frequency below visible frequencies, and Ks equals n squared, where Ks is the static dielectric constant. To summarize, the equation K equals n squared can be applied to the static dielectric constants of nonpolar materials only, or to the higher frequency dielectric constants of any dielectric. And that's from the University of Cambridge, okay? So that's www.doitpoms.ac.uk, okay? And more research is in the next video. Thanks for watching.